This week, we're going to talk more about matrix algebra and some of the important things we can do when we're doing matrix algebra. So the first topic is going to be about eigenvalues and eigenvectors. Eigenvalues and eigenvectors are ways of representing unique information about square matrices in particular, which we use a lot. And they satisfy this particular formula, which we'll talk a little bit more about. But essentially what this is saying is that a matrix times an eigenvector, a matrix multiplied by one of its eigenvectors, equals the eigenvalue times that eigenvector. So eigenvectors will always have k elements for a k by k matrix, and that matrix will have k perpendicular eigenvectors. And by perpendicular, we mean orthogonal. And we'll see what that looks like as well. The associated eigenvalues are ways of representing the proportional lengths of the eigenvectors. So the eigenvectors give a direction, and then the eigenvalues give the relative lengths of each eigenvector. We denote eigenvalues with lowercase lambda and eigenvectors with lowercase x. But as we'll see, the eigenvectors don't have an inherent defined length. The eigenvalues determine their proportional length, but they can have any individual eigenvector has infinite possible values for its length. It's really just a direction. So for practical purposes, what we often do is when we're just talking about the eigenvectors, we set their length to be 1, and then we refer to this as a normalized eigenvector denoted with E. So we can start by verifying the relationship between eigenvectors and eigenvalues. So let's say we have this matrix here at the top, A, and then we have this vector denoted E, which is 1 over root 2, and then negative 1 over root 2. First, the thing we can check is that whether E has length 1. And if you remember how to do that, we take the square root of E transpose E. And so here, just as a check, you can verify this for yourself. This vector does have length 1, so it satisfies the definition of a normalized eigenvector. And so first thing we want to do is multiply A times E to see what the matrix multiplied by its eigenvector is. And so to do that, we just do our matrix multiplication like we learned last week. And so you can pause here and work this out for yourself if you want, but I will show you the answer. So if we multiply AE, we wind up getting this vector, which is, of course, 2 by 1, since we're multiplying a matrix that is 2 by 2 by a matrix that is 2 by 1. So that leaves us with a 2 by 1 vector. So that's 6 over root 2, and then negative 6 over root 2. So this is pretty straightforward. We can probably pretty easily tell what the associated eigenvalue will be. So the idea is we want to find a scalar, a single number, that's multiplied by the original eigenvector, which is here. It's 1 over root 2 and then negative 1 over root 2. So what's a scalar that when we multiply by that vector gives us this same result, 6 over root 2 and then negative 6 over root 2. In this case, the answer should be pretty straightforward. It's 6. So if we multiply 6 by the eigenvector, we get the same result as if we multiply the matrix by the eigenvector. So therefore, our eigenvalue is 6, and our eigenvalue is 6, and our eigenvector is that should be 1 over square root 2, not 1 over root 2. That's a typo. I will fix that. So these should be square root of 2, not 2. But that satisfies an eigenvalue eigenvector pair. So the next question is, how do we get the eigenvalues and eigenvectors for a matrix to begin with? So we just verified when we have them, the relationship that they satisfy, but we haven't looked at how we can actually get the eigenvalues and eigenvectors of a matrix on their own. So the first thing we want to do is get the eigenvalues. And eigenvalues satisfy this relationship, where if what this is saying is essentially that if you subtract the eigenvalues from each diagonal element of your matrix, so if you subtract the first eigenvalue from the first diagonal element, the second eigenvalue from the second diagonal element, so on and so forth, and we get that by multiplying the eigenvalues times an identity matrix, which remember, if you remember what an identity matrix is, it's zeros on the off diagonal and ones on the diagonal. So anyway, if we subtract this matrix with the eigenvalues on the diagonal and zeros off the diagonal from the original matrix, we get a matrix with a determinant of 0. So this is, again, tricky to do by hand because getting determinants for larger matrices by hand is tricky, but we can do it for 2 by 2, and it will help us see what's going on. So let's start by getting the eigenvalues of this matrix, this 2 by 2. So the first thing we need to figure out is what values of lambda, or what eigenvalues, will satisfy this relationship such that when we multiply lambda times an identity matrix and subtract it from our matrix. So here we have lambdas on the diagonal subtracted from our original matrix, which gives us this. So it's the diagonal elements minus the eigenvalues, so that what relationship of what values of lambda would make this matrix have a determinant of 0. So recall that for a 2 by 2 matrix, we can get the determinant by taking x11 multiplied by x22 minus x12 multiplied by x21. So in that case, we are taking this times this and subtracting it from this times this. So that gives us 1 minus lambda, so times 3 minus lambda. So those are the diagonal elements subtracted from the off diagonal elements 0 and 1. And so that this zeroes out. So we just get 1 minus lambda times 3 minus lambda equals 0. And so we can pretty easily see what values of lambda will solve this. So it's any value of lambda that will make this little chunk here equal 0. And so here we see that lambda 1 is 1 and lambda 2 is 3. So those are our eigenvalues. So we can practice this with this matrix. And so we're going to start by setting it up the same way. So we need to subtract the diagonal matrix of lambdas. And so that gives us this thing over here. So now we need to take the diagonal elements multiplied by each other and the off diagonal elements multiplied by each other and subtract them. So that gives us 2 minus lambda times 3 minus lambda minus 2 times 1 is 2. So where can we go from here? So this isn't necessarily immediately obvious how we solve this the way it was before, because before we zeroed out this term. So one thing we can do, we can factor things out and then we can multiply things out and then try to refactor. So here I multiply out these parenthetical terms. And so that gives me 6 minus 2 lambda minus 3 lambda plus lambda squared minus 2, which becomes lambda squared minus 5 lambda plus 4. And so what can we do here? We need to try to refactor this. Do we see a factor solution that's clear? If not, and it won't always be clear. We could go back to our high school algebra and use the quadratic equation. We're not going to mess around with that here. There is an easy factor solution to this. If you don't see it already, it is lambda minus 4 times lambda minus 1. So set that equal to 0, and we get our eigenvalues. So once we have our eigenvalues, we can get our eigenvectors by solving for the original equation. So we need to multiply both the matrix and our eigenvalues by our eigenvector. So we'll call our eigenvector just x1, x2 here. So going back to the original matrix, the first one we looked at, the simpler one, we need to solve for this equality. So we need to figure out what values of x1 and x2 satisfy this relationship, and that will be our first eigenvector. So our formula implies following relationships. So if we multiply the matrix part out here, we get the first piece is 1 times x1, 0 times x2, and then the second piece is 1 times x1 and 3 times x2. And of course, this is just 1 times those. So we get 1 x1 plus 0 x2 equals x1. So that's not very interesting. We know what that means. But this one down here, this just says x1 equals x1. But here down here, we have 1x1 plus 3x2 equals x2. So this relationship has infinite possible solutions. So this is because eigenvectors don't have defined length, they only have a direction. So we can start by just setting one of our x's equal to 1 and then figure out what that would imply for the other one. So here we're going to set x2 equals 1. So if we do that, we get 3 times 1, 1x1 plus 3 times 1 equals 1. So that implies x1 equals -2, since we just subtract the 3, we move the 3 over here. This becomes x1. This becomes x1 equals -2. And of course, this satisfies the first equation as well. So we have our first eigenvector, x1 equals -2, 1. And so we want to normalize it so it has total length 1. Currently, it has length square root of 5. So if we square root x1 transpose x1, we get square root of -5. So if we want to get e1, which has length 1, we just divide by the length. So we divide x1 by square root of 5, and that gives us a vector of length 1. And you can verify that if you would like to do. It looks like it. I think that got cut off on this slide. That's okay. So what about the second eigenvector for lambda 2 equals 3? So what's the first thing we need to do here? Let's think about this. So we need to get our A matrix times the eigenvector equals this eigenvalue times the eigenvector. So that's what we've got here. So what does that look like? It looks like here's the A matrix, here's the eigenvalue. So we need to solve this equality. So we arbitrarily set x1 equals 2 again. So that implies 1x1 plus 3 times 1 equals 3 times 1. So we subtract the 3 times 1, we get x1 equals 0. And so we get 1 and 0. And note that this already has length 1. We don't need to do anything else. We're good to go here. If we want to do one more, we can get the first eigenvector from this matrix, which was, as a reminder, the first eigenvalue was 4. And so the answer is here. And you can verify that for yourself if you'd like. We can get the eigen-decomposition in R using the eigen function. So here I'm just importing this first matrix that we looked at into the eigen function, and you see it gives us the eigenvalues we obtained before, 3 and 1, and then the vectors 0, 1, and of course it doesn't write it as in terms of fractions and square roots. It gives us the approximate decimal. And here we see the same thing for the second matrix. So you can verify that these results match up to what we got by hand.